Okay, we are recording. So let me hand the floor over to group 10.
All right, good morning, everybody. Thank you all so much for coming. We really appreciate your support and your interest in our presentation. We are Hel10s Solar Solutions, and we're here today to present our heliostat module design. We are Mechanical Design Group 10. My name is Justin.
My name is Joshua.
Daniel.
My name is Jacob.
My name is Wasif.
My name is Robert.
I'm Malone.
Okay, first I'd like to take you all through our design motivation and our value proposition. We wanted to make a design that saves time and money through an economical heliostat design, and we accomplished that by primarily using low-cost, off-the-shelf parts wherever we could, including our PVC support structure and a minimal amount of motors while still actuating each mirror individually. Where we did have to manufacture parts, we made them as simple as possible so that way they could be manufactured without advanced machinery such as CNCs or anything that would be too expensive. And we wanted to focus on a modular design that really gave us a lot of ease of assembly and ease of replacement in any case where a part might be damaged or need to be replaced for any other reason. Now, first, really quickly, I want to take you through an overview of our product. As you all know, a heliostat is a mirror that moves in two axes to reflect sunlight at a central receiver to generate electricity. Our heliostat, like I said on the last slide, is designed to prioritize low cost and modularity while still achieving the customer needs of being a small scale heliostat that would be used in a much larger field to generate solar power in a solar thermal power plant. We achieve the customer needs using 4 subsystems. We have our structure subsystem, which is a PVC base, which is buried partially in the ground, which is modular, easy to put together, and inexpensive. We have a control subsystem, which is the ABS plastic box affixed to the structure subsystem that contains all the necessary electrical components that are used to control our motors. The movement subsystem are the 2 linear actuators behind the module, which tilt the upper frame, the 4 stepper motors that are enclosed in the gearbox below the mirrors, and the custom universal joint, which is used to allow for the tilting that we need from the linear actuators. And finally, the mirror subsystem, which are the 4 long rectangular mirrors that are affixed to drive rods, which can each be individually rotated in the azimuth direction. Our module has an overall height of 2.1 meters at the highest point and an overall width of 1.3 meters at the widest point. Some of the key features that really distinguish our design from the rest and make it unique and help it achieve our original motivation are the PVC frame, which, like I said, is very cost effective, very modular, and lightweight, allowing us to easily put it apart, take it apart, put it back together, repair it in any way that might be necessary. The custom 2-axis joint, which we did design and manufacture ourselves, this allows us to tilt the upper mirror frame in the necessary directions that we needed to tilt based on our movement subsystem. Our long rectangular mirrors, which are off-the-shelf parts, very inexpensive and easily mounted using a custom sliding system that we designed. So that way we don't have to worry about buying any kind of adhesives or backing, which would increase the cost and make them harder to replace. And finally, our movement subsystem, which utilizes a dual azimuthal drive, where the motor or the mirrors are tilted in azimuth by the linear actuators from behind, tilted in elevation also by the linear actuators, and then individually rotated by a dedicated stepper motor, which is enclosed in the gearbox.
So this overview is of the mirror subsystem. The focal point of this subsystem is the off-the-shelf glass mirror with aluminum reflective surface. This mirror was primarily chosen for its low cost of just $3.07 per meter squared when given a bulk discount from the manufacturer. The manufacturer will also CNC cut the mirror to the customer specifications, which saves both manufacturing time and cost. The mirror is placed into the slot on the bottom slot, which is fastened to the aluminum round bar, and then the top slot is secured over it. The slots have enough tolerance to keep the mirror in place, or they have a small enough tolerance of spacing to keep the mirror in place, but a large enough tolerance to not compress the mirror, even when considering thermal differences in thermal expansion between the aluminum slot and the glass mirror. The slots are also cast to reduce manufacturing cost. And the aluminum round bar connects to the movement subsystem on the bottom and connects to the structure subsystem on the top. Going into why the aluminum reflective surface was chosen, the two most prominent reflective surface materials in mirrors and heliostats alike are silver and aluminum. Silver has superior reflectance and optical quality, while aluminum has a slightly lower reflectance, partly due to an absorption band at 800 nanometers. Looking at the two materials for our heliostat, aluminum was chosen in one regard because silver is more expensive, so aluminum better aligns with our design motivation of reducing cost. Importantly, for an application such as this heliostat module, which is going to be used in a field with an installation lifetime of 20 years, a research paper showed that silver reflective surface used in a heliostat module showed surface degradation and proliferation of dark spots after a period of less than 1 year, which would cause inconsistency in performance over time. To have a more reliable and lower cost system, the aluminum reflective surface was chosen. To determine the number of heliostat modules required to meet the desired thermal input power of 1 megawatt from the customer needs, the following analysis was conducted. Assumptions were made on solar flux and optical efficiency based on information from the customer needs and an informational lecture from one of the clients. The known module collection area of 1 meter squared per module is plugged into the equation you see to determine that approximately 2,000 heliostat modules will be required to produce 1 megawatt of thermal input power. Another customer need is a concentration ratio of greater than 1,000. The concentration ratio definition that was used was the total area of the reflective field across all heliostat modules divided by the area of the receiver. While we were not asked specifically to design the receiver, we felt it would be useful to characterize the receiver size that would be required to meet this customer need. Knowing already from the previous slide that our total reflective area is 2,000 meters squared, to get a concentration ratio over 1,000, the receiver area must be less than 2 meters squared. We chose a receiver to define a receiver area of 1.95 meters squared, which gets us close to the limit enabled by the concentration ratio, while also having the larger reflective area helps minimize losses, which is ideal for this application. And with this area, the concentration ratio is 1,026. Performing an analysis was performed on the mirror to determine how well it could withstand wind loading. In doing this analysis, a safe operating wind speed was first defined based on background research on other commercial heliostats, which typically have a safe operating wind speed of 30 to 40 miles per hour. So a safe operating wind speed of 35 miles per hour was selected for this application. During safe operation, an assumption was made that for the worst case scenario of the wind load being perpendicular to the mirror, which would result in the greatest possible load. The tensile strength of glass depends on flaws, but background research showed that for high reliability applications, a value of 7 megapascals is acceptable for tensile strength. Calculating the wind loading from the air across the area of one mirror gives a value of 150 pascals. Modeling the mirror as a flat plate with simply supported edges, equations were found for max bending stress and max deflection. Constants alpha and beta are determined from ratios of the mirror's height of 800 millimeters divided by its width of 312.5 millimeters. Plugging into these equations gives a maximum stress of 0.2718 megapascals and a max deflection of 11.87 micrometers, which yields a safety factor of 25.8. While this may seem very over-designed from a safety factor perspective, the tiny deflection is ideal for mitigating tracking error from deflection caused by the wind loading.
Our control system uses a Raspberry Pi Zero microcontroller, which was selected for its low cost and wireless connectivity. The position of the sun is determined using an open source solar tracking algorithm, and the mirror's positions are adjusted accordingly. Because no sensors are used, the system is fully autonomous and requires no regular human upkeep. The controller housing is made of injection molded ABS plastic and houses the Raspberry Pi, motor controllers, and power converter that powers the Raspberry Pi and the motors. The housing is mounted to the PVC frame, and the wiring passes through the frame to protect it from the elements. A heat transfer analysis performed on the control box determined that the maximum interior temperature would be 83.2 degrees Celsius. This is below the maximum safe temperature for the electrical components of 85 degrees Celsius. This heat transfer analysis assumes that the outside surface is heated by radiation and cooled only by convection with the air, and that the electrical components within the housing are operating at maximum power with 90% efficiency. This analysis assumes a worst case scenario of very high outside temperatures, and it's expected that the interior temperature will stay below the maximum interior temperature that was calculated.
To introduce our movement subsystem, within the mirror frame subassembly, the azimuthal direction of each mirror slotted into the frame is actuated using a single dedicated stepper motor with 200 steps per revolution and a 1.37 Newton meter holding torque, all located in the protective housing at the bottom of the frame. A gear reduction is used between the stepper and the drive rod attached to each mirror to achieve a greater precision of movement. The elevation and the azimuth of the entire mirror frame assembly itself is then actuated using 2 linear actuator motors connected to the structure base with a 12-inch extension and 1,000 newtons of force in each. The linear actuators can be extended or retracted simultaneously to control the elevation of the whole mirror frame, or one can be extended and the other retracted to rotate it along the azimuthal direction. A custom manufactured 2-axis joint is used to restrict the motion between the structure and the mirror frame to the azimuth and the elevation axes to prevent twisting of the structure due to the linear actuators, as well as to support the full weight of the mirror's subassembly itself. For a total of 6 motors, all 4 mirrors can be rotated and elevated together, in addition to their individual rotations. We chose these 2 linear actuators as a means of preventing the individual mirrors from shading each other when the sun is at an angle by rotating the entire frame.
As mentioned previously, the custom 2-axis joint holds the entire weight of the mirror frame subsystem under certain conditions, and of course has to account for the rotation and general actuation of the mirrors. And because of this, it is deemed a very critical part. Specifically, the elevation rotation capabilities, which are facilitated through this joint pin, are found to be very important, because if this pin was to fail, not only could the system not be able to rotate in elevation, but also the entire weight of the system would collapse. And because of this, and keeping in mind wanting to preserve the design philosophy of less complexity and lower cost, we decided to try to optimize this specific part through using 6621 aluminum, and then accounting for the lowest acceptable diameter, and through a bending moment analysis and accounting for a factor of safety of 2, it was found that the minimum diameter for this part should be around 5.33 millimeters in the worst case scenario, and assuming rather unfavorable conditions. And so we chose the actual pin diameter to be around 6 millimeters.
Gear reduction is used between the stepper motors and the mirror control rods to control the maximum step size to ensure that we're able to meet the customer requirement that the heliostats track the sun throughout the entire day. Assuming the maximum receiver height of 100 meters and the maximum heliostat module distance from receiver of 100 meters, if we make those assumptions, then the maximum, without gear reduction, if the motors were directly mounted to the rods that control the mirrors, the reflection translation would be 4.44 meters per step. With the 6:1 gear reduction, that translation is reduced to 0.74 meters per step. With our designed 1.5 meter wide receiver, this means that the reflection of the sun can be continuously maintained on the receiver at all times, even for the heliostats that are furthest from the receiver. Using a 6:1 gear ratio also reduces the torque load required of the motors. The motor mount that holds the stepper motors and supports the mirrors is constructed of 5 pieces of welded 6061 T6 aluminum. A deflection analysis was performed to determine the required cross-sectional geometry so that the maximum deflection would be 1 millimeter. 1 millimeter was chosen as a value that would minimize any tracking losses due to the deflection of the motor mount. Our original concept for the motor mount had a single piece of aluminum, and our analysis found that to have a deflection of 1 millimeter, that single piece of aluminum would have had to be 21 millimeters thick. This meant that we had to increase the stiffness of the motor mount by changing the cross-sectional geometry, which, as you can see here, now has a channel shape facilitated by the 3 pieces of aluminum that are welded together. The motor mount was modeled as a cantilever beam with loads from the motors and the mirrors, as well as a load from the weight of the aluminum itself. The length of the beam is constrained by the mirror geometry, so the profile of the cross-section had to be changed to ensure that the maximum deflection was 1 millimeter. The cross-section was adjusted until the required moment of inertia was less than the designed moment of inertia, which resulted in the profile shown on the slide, with the top piece of aluminum being 6 millimeters thick and the side pieces being 30 millimeters tall and 4 millimeters thick.
In our structure subsystem, the upper crossbar of the mirror assembly that holds the drive rods attached to each mirror in place and provides the mounts for the linear actuators connecting to the structure from the mirror assembly were constructed out of 25 millimeter diameter PVC pipes fit together due to the low cost, the modularity, as well as the lightness of the material, which decreases the acting load of the weight on our structure and linear actuators, allowing a greater ease of movement of the mirror frame with less force from our motors.
To introduce the base of the structure subsystem, this part directly fits into the ground and then attaches to the linear actuators and then the central universal joint, which holds the mirror frame subsystem. On the bottom of the visual as shown, there are 4 vertical PVC pipes, and these are designed to supplant into the ground, which we found was an efficient way to secure the whole subsystem. And then on top of it, there's the square PVC structure, which is held together through elbow joints. And the 4-way elbow joints as seen near the back of the design were designed to hold the linear actuator mounts without any bending on the PVC itself, because supplanted this position, there are essentially only compression forces on the PVC pipe and the joint, as opposed to the PVC T-fitting, which allows for some deflection on the front end of the PVC, but as accounted for, this was not a problem based on the dimensions of the PVC. Overall, this fits the design motivation of wanting a low cost and easily manufactured along with a modular design. And the PVC and on-the-shelf parts really facilitated this and allowed for this part to be easily fit together.
For our structure subsystem, we found an important analysis to conduct was that of the bending stress of the PVC at the custom 2-axis joint, as this joint acts as a critical load-bearing part. To accomplish this, we treated the PVC pipe where the U-joint connects to the mirror assembly as a beam with a length of 284.4 millimeters that is simply supported at both ends. This beam has a point load F due to the total weight of the mirror assembly, including the motors, the gears, fasteners, and brackets, when the mirror is in its most vertical, when it's rotated in its most vertical position, as the majority of the load will be concentrated on a single support. We assume this to be the worst case scenario of loading. Knowing this concentrated load from the mirror weight to be 273.5 newtons, the bending moment of the force was calculated to be 77.8 Newton meters. The moment of inertia of the hollow PVC pipe was calculated knowing the inner and outer radii to be 2.92 10 to the negative 7 meters to the fourth. Knowing this, the resulting bending stress on the PVC pipe comes out to be 8.05 megapascals. And dividing this into the known yield strength of PVC, this returns a factor of safety of 6.86. This confirms our selection of PVC piping as an ideal low-cost material for our structure subassembly.
A heat transfer analysis was performed on the PVC in the base to make sure that it would not exceed the melting temperature of PVC. We assumed that the ambient temperature was 105 degrees Fahrenheit, and we got our number for the sun's radiation for Las Vegas's latitude in the summer. The analysis only considered radiation from the sun and convection with the air around it, not convection with the ground. From our analysis, we determined that the maximum operating temperature of the PVC would be 87 degrees Celsius, which is well under the melting point of PVC. We also performed a lifting force calculation on the mirrors when they're folded into their safety position under high wind loading. Some of the important assumptions we made were that the maximum possible wind speed would be 40.2 meters per second, and the max angle of attack of our mirrors is 1/2 degree. From our calculation, we found that the lifting force was 54 newtons, and the module weight being 274 newtons yields us a factor of safety of 5.05, which we determined was sufficient to say that the force from the wind will not lift the module out of the ground. We were able to reduce the prototype price to the mass production price, considering some bulk buying scenarios. For example, we put a 25% discount on all of our OTS parts and raw materials for buying in bulk. We were also able to save on shipping costs, due to the fact that since we're buying in bulk, the price of shipping per module will be less. However, the only place we were able to save in the manufacturing labor, assembly labor, and energy consumption categories was from bulk ordering some of the 3D printed parts that we needed. Overall, the reason why our price for the module is expensive is due to the fact that the motors before any price reductions accounted for $125, and after including bulk buying discounts, it still accounts for nearly half of the mass production price just from the motors.
So in order to quantify the availability of the technology used in our design, we assessed our module with the technology readiness level scale. And looking at all the components, the custom 2-axis U-joint was assessed as scoring the lowest at a level 3, where the concept demonstrated analytically or experimentally. This is not a abstract new design, but it does require physical testing to ensure its sufficient performance in the expected conditions. And in order to attain the customer need of mirror surface cleaning of at least 95% reflectance recovered after cleaning, during research, a study was found that high pressure stream of water recovered 95% of the reflectance, and the 500 PSI was determined to be at the nozzle exit, and our module design was able to withstand the mirror surface cleaning process.
To summarize our heliostat design, we believe that the notable aspects of it include the PVC frame, which is low cost for its ease of use and strength. And along with this, there are a low number of motors per mirror, given that the 2 linear actuators are able to actuate the elevation rotation of all 4 mirrors, along with the 4 stepper motors, which can more finely actuate the azimuth of the mirrors. On top of this, we believe this ties into the high precision of the mirror control we have in our system, given that there are 2 modes of azimuth rotation via stepper motors and then the linear actuators, which was done like this to avoid shading under certain circumstances. And on top of this, the stepper motor reduction involved in the gears increases the accuracy of the azimuth rotation on the individual mirrors significantly.
Conclusion, we felt that our module benefited from being low cost, easy to manufacture, and having a modular design. And with that, I think our presentation is over and we're open to questions.
Hey guys, this is Tom Singer from Northrop Grumman. I wanted to ask, you've got 4 mirrors that are all fairly close to each other, right? What's driving having individual control of those mirrors? Because they're all pointing, they're reflecting one sun to one collector, and I wouldn't expect they're far enough apart that they would need to have independent control.
I think I can take that. Part of why we have independent control for each mirror is the way we had interpreted the customer need of 4 heliostats per module. We didn't realize, we thought that a heliostat was defined as something that could track the sun with independent actuation. So that forced us in our design process to have individual actuation for each mirror.
How did you interpret the customer's need of $100?
We tried to, as best as we could, to get our price to be under $100, but just given our design, we couldn't find a way to do it.
If we opted for something other than linear actuators, we might have been able to bring the cost down. So perhaps earlier in our design process, we should have thought more about that and thought of either an alternative to a linear actuator or found some way to manufacture or purchase a cheaper linear actuator, because the linear actuators are definitely the most expensive component in our design.
Mm-hmm. But the stepper motors aren't cheap, and you've got 4 of them to control individual mirror azimuths that you're also controlling by your 2 linear actuators, right? So it seems like there is some unnecessary redundancy in your aiming capability. And I would suggest that if you've got if you're having trouble meeting the customer's cost, which is 9 times out of 10 going to be their primary requirement, if you're having trouble meeting the customer's cost, you may have to compromise somewhere else.
That is true. One of the reasons why we have so much control over the mirrors was so that we would not have any shading on the mirrors, which was a customer requirement. but we could have also tried to make our design so that we wouldn't have to be able to control the mirrors as much individually to eliminate shading, where we could have eliminated, we could have reduced the cost, or we could have tried to compromise on a different customer need.
Okay. Let's see. I'll say I really appreciated the structural analysis that you were doing. I appreciate the hand calcs on the mirrors. I saw a flat plate analysis, which I don't know if you found that in Aurora or somewhere else, but good job on that. When you were talking about, you've got a minimal deflection on your mirrors, so you're not worried about tolerance on your aiming. The compliance of your mirrors is not going to be the only thing that affects your ability to aim, right? So your module is sitting 100 meters potentially away from the base of a tower and a collector, some distance up. So let's say it's 100 meters up. You've got to precisely aim a ray of sunlight over a distance of 141 meters, right? So the overall compliance of your structure is going to come into play in how accurately you can point the sun back to that collector. Have you considered the overall compliance of your structure?
We are currently in the process of calculating that for the FDR, but we haven't gotten a final total compliance yet.
Okay. Yeah, I think that's going to be critical. Let's see, what else do I have? You're building this out of PVC pipe that's being fit together. And in my experience assembling PVC pipe, and I'm certainly not an expert at it, but in my experience, it's not a very precise process. Where you've got the mirrors, especially where you've got the mirrors connecting to those horizontal rods at the top, how accurately are you going to be able to control the positioning of the slots that those mirrors fit into as you're assembling PVC, either in a shop or in the field, I suppose?
I think one thing that helps with assembling the PVC is that while some of it is just off the shelf, there are other parts where we have to, say, drill holes into them or cut them to very precise lengths. And that definitely helps in fitting things together. But also if there is a little bit of discrepancy in the design in terms of just dimensions, the way the linear actuators are set up, being that there are two omnidirectional universal joints on either end, it does allow for just individual actuation of each heliostat in the event that there is, discrepancy.
And then one more thing that I was discussing with Brad kind of offline yesterday as we were watching some of these other presentations. Las Vegas gets not infrequent hail events. So I guess what is your capability of withstanding impact from quarter size hail? Because that was a very common. I found a link that had like hail history in Las Vegas, and quarter size hail came up pretty frequently.
Obviously, when you have a module with giant pieces of glass on it, hail obviously isn't a very favorable condition. We did purposely design it, however, so that it is very modular, so parts can easily be replaced if they need to at very low cost. If anything on the structure were to break, it's just PVC, so you can easily just pop that part off and put it on a duplicate part, which would be cheap. And then with the mirrors, we have a custom slotting system that allows them to be easily removed with just loosening one bolt, so that you can easily replace the mirrors, which are also low cost off-the-shelf parts.
So similarly in the case where, as Justin had mentioned, we can remove the mirrors themselves to prevent them from being damaged. But we had designed this for.
How long is that going to take when a storm pops up with hail and you've got, I think we said like 2,000 of these, each with 4 panes of glass on it?
We would have to take a look at the handling time and manufacturing, which is in progress for our FDR. But hopefully we can get that down to, but similar to just removing the mirrors, we also have, it was designed as like a wind safety in case there were heavy wind forces, but the whole mirror frame can be using the actuators flattened, and each individual mirror can be rotated 90 degrees to kind of, can be rotated to be sideways to kind of minimize the area of contact that hail would hit the mirrors with. But that's in like the
Right.
worst case scenario where we can't get the mirrors removed in time.
That's a pretty clever solution. I'd say that's much more feasible than taking off 8,000 mirrors.
Yes.
What was the motivation for going with 2 linear actuators instead of trying to put one in the middle and just getting away with one?
So the reason we have 2 is so that the linear actuators can provide rotation in the azimuth and elevation. If we had had 1, we could have easily controlled the elevation, but not easily controlled the azimuth. And one of the important features is that the linear actuators can rotate the module and the azimuth so that as the individual mirrors are rotating about their own axes, we don't have any shading from one mirror on the other because the entire frame can rotate so that it has a more advantageous position with respect to the sun. Does that answer your question?
Yeah, I hadn't thought about it being rotated in that way. I thought they were going to be extended and retracted at the same rate. So yeah, that's a good way to maximize your mirror area. Yeah, so yes, it does answer my question. In one of your other calculations, you were showing how much stress and deflection you would have at 35 miles per hour. Kind of similar to what Tom was getting at, if as far as compliance elsewhere in your structure, it would be good to see with a given deflection or how much impact that would have on your ability to target the collector. And maybe what your maximum deflection you could tolerate is on the mirror, and then also compliance-wise in the structure. Both the deflection and the stress looked pretty small, so I would say you could go ahead and try to crank up your input wind speed to 40 to 50 miles per hour, and just kind of quote those numbers instead of limiting it to 35 miles per hour.
That's a very good point because it's definitely better to quote the highest numbers that we can, if you will. And as far as for the compliance, yeah, currently our analyses are based on analysis of individual components or subsystems. We should do an analysis of the overall structure to determine the compliance.
I think that's a good idea because your overall structure is going to contribute to your ability to aim.
And then similar thought on the drag force that you calculated, or sorry, the lift force that you calculated. I was thinking it'd be good to look at drag force as well, and check that your structure is able to withstand that as well. The only other thing I have is for your gears that are on the bottom. There are some images that showed that bottom section of that enclosure open. Is that just for presentation purposes, or is that going to be open to the elements on the bottom side?
As of now, it is designed so that the bottom face would be open to the elements, but if that would be a problem, we could add more sheet metal on the bottom to fully enclose that. There is room for it.
Okay. I guess I have two more things. Unless someone else has a question, I can come back to it.
Oh, go ahead, Brad. We've got about a minute left.
Okay.
So
Yeah. I hit another team with this question. I was concerned about being too close to the ground with the mirrors due to the likelihood that you're going to just have more sand blowing in the wind when you're closer to the ground, and that will kind of degrade your surface. So I was wondering if there's any thought put behind how tall this should be and how far above ground level it should be.
It was thought that the vertical PVC pipes at the bottom that fit into the ground, that those could be adjusted slightly. So under certain conditions, we thought that it could just be set so that the square part of the base just touches the ground, so it's kind of flush. But under other circumstances, we thought, due to uneven grounding, that it could be elevated to a certain degree, and there's some leeway on that, since like the lifting forces are not extremely significant given how strong it'd be supplanted in the ground.
Okay. Yeah, that would be an easy solution. Those are your thicker parts of your structure too, so extending those shouldn't cause a problem. And then I'm not sure if I heard it correctly when you were talking about modularity and replacing parts. It sounded like you said you could pop apart some of the PVC. I'm assuming if it's PVC, you'd be bonding your PVC together as you're assembling it. So that if that's the case, you wouldn't be able to take those parts apart. You'd basically have to cut away that section of your structure and kind of put in like a splice joint to put those pieces back together.
Yeah, we felt that if like the PVC is a rather strong part of the design, so more so the mirrors would be modular. But if need be, like under certain circumstances, technically we could, replace the PVC with a very similar part.
Okay. So you were mainly talking about the fastened pieces rather than the PVC itself.
Yeah, like the main advantage of the PVC is that it's easier to assemble, I suppose, because it's easy to line up and then you just put some adhesive on it and stick it together.
Right. Yeah, cost and ease of assembly. Okay, thank you.
great. Okay. Well, we are just a couple minutes over, and I want to make sure that we don't eat into our break too much or overtax the team. So I want to wrap it up there. I want to thank you guys for sharing your design and your presentation with us. It's this afternoon now. I was gonna say this morning, but we passed into afternoon in the midst of your talk. And I think I've already mentioned this to you guys in design reviews, but I'm a big fan of PVC. So I've got a ton of it just cut to various lengths out in my garage. And anytime I need to prototype anything, the first iteration is just to put it together with PVC. So I appreciate that you guys, kind of took that idea and ran with it and did all the analysis to make sure that it wouldn't get too hot or get, too far bent out of shape so it would deform and stuff. So I thought that was a good aspect of the design, was to use that as an inexpensive yet robust building material. So I appreciate that. All right. With that, we are in a 45-minute lunch break. So I think the plan is to reconvene at 1. Make sure I've got that right. Yeah, the plan I think is 1 p.m. Back in Zoom meetings. There'll be an Aero presentation then. So we'll see everybody at 1 o'clock. And with that, I'll stop recording.